Hello everyone, this is Han Zhao from Shanghai Jiao Tong University. The topic of my presentation is exploiting intra-SM parallelism in GPUs via persistent and elastic blocks. Recent years, deep learning makes great progress in many fields, such as CV and NLP. The heart of deep learning is general matrix multiplication, which has many related kernels: FC kernel, convolution kernel, and encoder in BERT. Due to the importance of a gem, tensor cores are built to accelerate it. As shown in the figure, a GPU equipped with tensor cores provides higher arithmetic throughput. Although tensor core is the new computing resource, its programming also confronts to the general programming mode. As for GPU kernel scheduling, there are two parallel interfaces, which are CUDA stream and MPS. They are kernel-level scheduling and do not perceive the kernel type. In order to discover the potential parallelism with CUDA stream, we customize two kernels. Task A is adapted from the NVIDIA sample code. Task B performs pure computation using registers and does not perform any memory operations. We define the metric overlap rate to measure the degree that two tasks are processed in parallel. The experimental results are shown in the table. It is easy to infer that there is potential parallelism if the co-running kernels use different processing units. We then investigate whether real applications can benefit from the parallelism. Task A is also the NVIDIA official gem kernel, and Task B is the kernels from Parabol. As shown in the figure, all collocation pairs have low overlap rates, and CUDA stream could not exploit the two hardware's parallelism directly. The reason behind the low overlap rate is CUDA stream's kernel-level scheduling. Only when all the blocks of a task are launched on the SM and the SM's resources are not used up, another task's blocks could be scheduled on the SM. As shown in the right table, we profile the kernel's resource usage on the SM. Among these 16 tasks, 14 tasks occupy all the thread slots, 10 tasks require shared memory, and 13 tasks use more than half registers. Therefore, it is easy to infer that there are two challenges to exploit two hardware's parallelism. First, resource contentions between kernels. Second, runtime scheduling for different kernels. Therefore, we propose Parallelism to exploit the Intra-SM parallelism for maximizing the GPU throughput. It comprises of three modules. Source-to-source compiler solves the challenge 1, offline strategy customizer and online scheduler solve the challenge 2. As discussed before, GPU kernels often use a large number of blocks to hide the slow cycles due to data access. After experiments, we find that it is not always necessary to do that for a kernel to achieve high performance. Therefore, we adopt the persistent block technique to solve the thread slot contention. As shown in the figure, we conduct the experiment after they are transformed to persistent block mode. The overlap rate of 6 benchmarks increased significantly, while others are still low. Besides the thread slot contention, kernels still contend for memory resources. While tensor cores can only perform gem tasks, its shared memory usage could be calculated with these equations. And it is easy to find that shared memory has a linear relationship with the block size. When we reduce the block size, the tile size becomes smaller, and the shared memory usage reduces. We refer to the kernel with smaller block size as the kernel's elastic block version. Besides TC task, experimental results show that 13 of 15 CD tasks in Parabol support block size adjustment. We also conduct the experiment after all the kernels are transformed to elastic block mode. While co-running with elastic TC task and normal CD task, the overlap rates of 6 benchmarks increase. While co-running with elastic TC task and elastic CD task, the last 3 benchmarks with blue bars exploit the parallelism. Persistent and elastic block provide several versions for each kernel, and they have performance difference. The offline strategy customizer customizes the scheduling strategy for mainstream TCCD kernel pairs. For TCCD kernel pair, we need to search for the optimal configuration pair among all possible ones. A complete search requires O(n) score time complexity, which is unacceptable. Therefore, we reduce the overhead from two aspects. First, we reduce the elastic block version of each kernel due to performance differences. Second, we make corresponding judgments based on resource utilization. While the offline strategy customizer locates the optimal co-running configurations, the online scheduler makes kernel scheduling decisions at runtime. Specifically, the online scheduler first identifies the possible TCCD kernel pairs based on the kernel's dependencies. Second, the scheduler selects the kernel pair with the largest overlap rate based on the profiling information. In the evaluation, we choose 5 commonly used DN models as the tensor core task, and we use all the 15 applications from Parallel as the CUDA core task. The hardware is the NVIDIA 2080 Ti. This figure shows the system-wide throughput improvement with plasticine compared with the CUDA stream. Plasticine improves the throughput in all the 75 pairwise collocation pairs. Plasticine also increases the throughput by 15.3% on average and up to 40.2%. The figure shows the execution trees if TC task ResNet 50 and CD task FFT with plasticine and CUDA stream. The first row represents the tensor core active time, and the second row represents the CUDA core active time. In these two rows, we used blue color to represent the co-running time. Finally, conclusion. Plasticine proposes persistent and elastic block to solve resources contention. Plasticine uses the compilation stage and the runtime schedule to exploit the Intra-SM parallelism. That's all. Thank you.